I think Abby is next. We have Abhisek Sahu from currently in India, so I think it's after midnight for Abby, and he'll uh, he'll tell us about holographic cosmology featuring black holes. So go ahead.
All right. Yeah. Am I audible?
Yes.
Okay. Thanks. So today I'll focus on the parts of my work that address cosmological spacetimes using holography. And particularly, talk about my joint work with my advisor, Mark van Ramstonk, and other collaborators at UBC. Um, okay. Yeah. So a broad question that motivates much of our community is how to build a quantum gravitational description of something like our own universe, one that looks approximately homogeneous and isotropic and shows accelerated expansion. And the simplest effective explanation that's often given is that we just need a positive cosmological constant. However, our best understood theories of quantum gravity are in the context where we have a negative cosmological constant in the form of ADS-CFT and holographic theories like that. And in fact, negative lambda gravity or gravitational effective theory admits many interesting cosmological solutions. For example, if I just take your favorite holographic CFT and then choose its vacuum state, it describes pure ADS. And now, if I take any spatial slice and inject uniform energy density onto it, its causal patch becomes a cosmological spacetime with Big Bang and Big Crunch singularities. So, a nice question that one could ask is restricting to such negative lambda cosmological solutions, could we understand some general features that carry over to other more realistic settings? And this approach is kind of parallel to how we have learned so much about the unitarity of black hole evaporation by studying black holes in ADS coupled with thermal baths and so on, even though the original paradox was framed in flat space time. Okay, so um, in ADS-CFT, finite energy CFT states correspond to bulk geometries that are asymptotically empty. However, cosmological spacetimes are anything but empty. In fact, they have uniform matter distribution throughout. So a natural compromise would be to work with spacetimes that contain a finite cosmological region in the middle, but still remain asymptotically ADS. So in the past, I have worked on two such explicit constructions. One with a spacetime where we have just a single asymptotic boundary and a FRW region in the middle, and a second one in which we have multiple asymptotic regions built from a uniform lattice of black holes whose interior forms a cosmological region. Obviously, these spacetimes are not globally homogeneous and isotropic, but that's fine for our purposes since they are locally cosmological and they can describe what a single observer would see along their causal trajectory, which never intersects or interacts with the asymptotic region. So, in the rest of the talk, for the sake of brevity, I'll just focus on the second model, which I call the black hole cosmology, and talk about some of the general lessons that we can learn by studying that. So let me just describe what this geometry looks like. So we start with a two-dimensional spatial slice that is locally hyperbolic and contains a regular lattice of black holes. So each black hole has a second asymptotic region. And so the full 2 plus 1 dimensional geometry it's a so-called multi-boundary wormhole in ADS spacetime. And this gives so the interior of the space-time, which by which I mean the region which is bounded by the event horizons of all these black holes, resembles a cosmology supported by a uniform distribution of black holes. And this is very much like our own universe. So, for example, if a observer within the within the cosmological region would experience an approximately uniform distribution of something like galaxies with a black hole at its center. I mean, this is very rudimentary, but it has the same features. So in this picture, I have shown the spatial slices to be closed on the left here, but on the bottom, you could also arrange your black holes in a way that the slices are open, and you could close them up again by doing some kind of periodic identifications. From the boundary point of view, every asymptotic region here, corresponding to every black hole, has a two-sided has a it can host a CFT, and so I guess like there would be a multipartite entangled state of the CFT that describes geometry. So in order to understand better what the properties of this state are, it's useful to pass on to a Euclidean description. And so there we'll utilize this fundamental key fact that any Lorentzian negative lambda cosmology has a time reversal symmetric slice, which admits a Euclidean continuation about its time reversal symmetric slice. And so the analytic continuation here of a Big Bang, Big Crunch cosmology gives me instead a wormhole, which has an asymptotic boundary in the past Euclidean, in the Euclidean past and in the Euclidean future. So from the boundary perspective, if I just began with two CFTs, I would not recover these wormholes unless I introduce some kind of correlation between these Euclidean CFTs. And subsequently, I'll talk about how exactly in this black hole cosmology model we have certain correlations that helps us get the cosmology. So, okay, let's now look at the Euclidean picture. So on the left here, on top in green, I've shown a spatial slice of our black hole cosmology. Now, if we analytically continue this geometry, each black hole's second asymptotic region, which is kind of this end at the end of this downward funnel, it evolves into a tube that joins the future and past boundaries generated by the cosmological interior. So without the black holes, we would simply have two disconnected boundaries. But with the lattice of black holes present, the full Euclidean boundary, which is shown in the gray on top right, becomes a higher genus surface built from a network of tubes connecting the future and the past. So now if we place a CFT on this manifold, each tube effectively introduces some kind of interaction between the CFT and the past slice and the future slice. Furthermore, by cutting this manifold at the time reversal symmetric slice, we can prepare some state. And this would be something like a thermofield double state, but generalized to multiple different CFTs, which is prepared on the CFTs, which is exposed by cutting the slice. Um, right. So yeah, and you could take so this would be sort of the preferable state that this of the CFT is something like a Hartle-Hawking state. You could also take an analogous viewpoint. So instead, if we integrate out these tubes, then so each tube sort of introduces a thermofield double kind of interaction between the future and the past, which is same as saying that we introduce a bunch of operators with some thermal weighting in front of them. And so integrating out all the tubes gives me some kind of ensemble of operator insertions between the future and the past. And another gravitational picture corresponding to that would be a cosmology, which we should think of as a superposition of many pure state cosmologies or a mixed state cosmology in general, which does have these black holes, which are denoted by these event horizons, these dotted lines on the bottom left. However, we do not specify anything beyond the horizon. So the tubes coming from the second asymptotic region sort of provide a particular purification of this mixed state cosmology. It is also interesting to note that the cosmological saddle is only one of other possible saddles. So in this Euclidean picture, the cosmology fills the space between the tubes. We could equally have some kind of saddles which fill inside the tubes. And so an analogous story like the Hawking page transition is possible here. And we could ask, when does exactly the cosmology dominate? And since we're in 2 plus 1 dimensions, we have enough analytic control to answer that question pretty much exactly. And we find that for the cosmology to dominate, we need these tubes to be sort of large, so ADS scale, which is not ideal. Like ideally, we would have like them to be small and numerous so that it corresponds more nicely to a uniform and isotropic cosmology. Um, okay. So now it's time to draw some general lessons that emerge from this picture. So the first thing is that this cosmology should be thought of as being in a mixed state, and and the purification is provided by these auxiliary degrees of freedom. So in this case, these were the second asymptotic regions with the CFTs. In this sense, this auxiliary systems play a role very similar to observers that have been introduced recently in explaining some features of a closed universe. So in this case, the auxiliary systems provide a large Hilbert space within which the cosmology exists. People have also introduced certain rules for the quantum mechanics of the observers in this closed universe, which allows it to access a large Hilbert space, even though it's believed that the closed universe has a one-dimensional Hilbert space. And so in this black hole cosmology model, a question that I'm interested in understanding is, how does this observable rule actually play out? And this would be a nice sort of higher dimensional check in which the observers are sort of naturally included in the picture instead of being put in by hand. And also, this would be higher dimensional, whereas most of the observer rules are most well understood in 2 dimensions. Secondly, I would like there is a preferred state provided by Euclidean path integral, and this is somewhat analogous to a Hartle-Hawking state. Instead of having a no boundary, we have a very complicated, like higher genus boundary, or yeah. Furthermore, this cosmology is highly entropic, so there must be required a high degree of correlation between the Euclidean past and the future boundaries for the cosmology to dominate. And so that just tells me that the cosmology actually has a lot of entropy. Right. So this is also this bubble of cosmology is another project I did with Mark and Peter
Like
Simigia.
2 minutes.
Okay, thanks. I'm almost done. And so this is a much simpler model in which we just embed a bubble of cosmology within an asymptotically ADS spacetime. But many of the features and the general lessons that we saw in the previous case are visible here as well. I'm happy to go into more detail in the question section. Finally, I would just also like to point out some other directions that I'm interested in. So So beyond cosmology, I'm interested in understanding what is the structure of subsystems in quantum gravity. And so recent proposals by Bousso and Pennington have defined generalized entanglement wedges, which could exist in any arbitrary spacetimes, including cosmological spacetimes. And these regions satisfy many properties which are analogous to standard entanglement wedges at ADS-CFT, and particularly they have generalized entropy that satisfies strong subadditivity. And this is a key feature that we expect from finite dimensional quantum subsystems in just ordinary quantum mechanics. So unlike ADS-CFT, however, what is the underlying mechanism and what's the underlying reason for these generalized entanglement wedges to behave this way is unknown. So in this recent work with Jeremy van der Heijden, Rana Zibaksh, and Mark van Ramstung, I um, formulated candidate von Neumann algebras for such wedges and also tried to suggest how an algebraic RT formula could be associated with these wedges that explain these properties of strong substitutivity and monotonicity. And I would like to just end on the note that ADS-CFT is a useful tool and that has taught us many explicit things about quantum gravity. And in future, we are learning some tools such as this von Neumann algebras, which are sort of model independent. And so in the future, it seems like it would be a nice thing to use such tools to abstract out the lessons that we learn from ADS-CFT so that we could apply to more general systems. Thank you for your time.
Okay. Okay, so again, we're right at the time limit. If there's one question, we could squeeze that in. Okay. Um, okay, if not,